I want to give you a primer in molecular orbital theory so that we can talk about some of the other concepts in this course. So molecular orbital theory is another theory of describing the bonding that happens in molecules. I'm going to focus on pi systems in this particular case. So we're going to try to describe the bonding that we see in a carbon-carbon double bond, something as simple as ethylene. So we know that this pi system is made up of p orbitals. So another picture that we could draw for this would be two p orbitals that are bonded together. We have the sigma bond in the middle, but we're focusing on this pi bond that's on the outside. And how these pi bonds line up and whether they are in phase is going to determine the bonding that we have in that particular case. But if we want to try to describe what's happening here, instead of using the atomic orbitals, we can use something called molecular orbitals. And one thing we have to remember is the number of atomic orbitals that we start off with in the system is equal to the number of molecular orbitals that we're going to end up with. So in the case of something simple like ethylene, we have two p orbitals. That's our atomic orbitals. So we have two p orbitals. And each of these p orbitals is going to have one electron in them. So in the end, what we're going to end up with is two molecular orbitals. And we'll have to look at where the electrons get placed in these molecular orbitals. So if we try to see how these things can come together, here we have one p orbital. Here we have another p orbital. Now there's two ways that they can combine together. They can combine together in a constructive fashion. And what we mean by that is that the phases of the sides of our orbitals are complementary, or they can line up in a case where those phases are not complementary. What we have is a constructive and a destructive interaction. So here we have a constructive interaction, and here we have a destructive interaction. And what we notice is, in this case, there's an extra node in this particular molecule. Now here, if we have favorable overlap, that's telling us that we can have overlap or a good bond between these two carbons. If we have a node, that means there's zero chance of finding an electron at that position. So this complementary interaction is going to be a bonding molecular orbital, and this destructive or uncomplementary interaction is going to be called an anti-bonding molecular orbital. Now when we fill these molecular orbitals with electrons, we always go from the lowest to the highest. So we're going to pair up our electrons here. So this tells us, in the case of ethylene, that the electrons are sitting in this bonding molecular orbital. So if we expand this to a larger system, such as butadiene, in the case of butadiene, we have 4 atomic orbitals. So that means we're going to have 4 molecular orbitals. And if we wanted to, we could try to figure out what those different molecular orbitals are going to look like. So we're going to have 4 different cases. And if we look at how these line up, in the lowest energy state, all of these orbitals are going to be in the same phase. So that means that we're going to be able to find electron density over this entire sequence. If we look at the next energy level, then we've added one node inside of this system. We have one node that ends up right here in the middle. Once we go to the next one, we're going to add a second node. And then finally, with the last one, we end up having 3 additional nodes. So none of those orbitals are going to be overlapping with their neighbors. Now we can assign names to these. That lowest energy state we're going to call psi 1, psi 2, psi 3, and then psi 4. If we had 4 atomic orbitals, these are 4 p orbitals coming into our system. That means we have 4 electrons. So if we think about the energy levels here, we're going to fill up those bottom 2 energy levels. The top 2 are going to be empty. So these bottom 2, we're going to call our bonding molecular orbitals. And those top 2, we are going to call anti-bonding molecular orbitals. The 2 that are at the interface have some special names that we need to know. So this is the highest energy level that has electrons, the highest occupied molecular orbital, or HOMO. And the one right above it, psi 3 in this case, is the lowest unoccupied molecular orbital, or LUMO. So recognizing the HOMO and the LUMO in a system is going to be important for some of the things that we're going to talk about. So this is a good MO theory primer that we'll be able to use when we talk about something like UV spectroscopy in the next video.